For almost a million years, Earth's climate has been doing something incredible. It's been pulsing, almost like a heartbeat, swinging between deep freezes and periods of warmth. You could say it's one of the most fundamental rhythms of our planet. Today, we're going to play detective. We're going to look for the clues that solve the great mystery of what really drives Earth's ice ages. All right, let's get into it.
So let's start with the big one, the question that stumped scientists for more than 100 years. What on Earth, or off it, is powerful enough to plunge the entire planet into a deep freeze and then do it again and again like clockwork? Well, as we're about to find out, the answer isn't some random disaster, but a beautiful, predictable dance happening out in space.
You know, our first huge piece of evidence comes from a really amazing place, deep inside the Antarctic ice sheet. Scientists have drilled down miles deep to pull up these ice cores, and trapped inside are tiny little air bubbles from ancient atmospheres. It's literally a library of past climates. And when they analyzed them, the data showed this unmistakable pattern going back 800,000 years, a long, rhythmic pulse between deep ice ages and the warmer periods, kind of like the one we're in right now.
Now, the thing that really blew everyone's minds was just how regular this cycle was. It just didn't feel random, like a bunch of volcanic eruptions. It felt deliberate, like a clock. And that realization forced scientists to look up, away from the Earth itself. The pacemaker for our planet's climate wasn't on the ground. It was in our planet's journey through space.
And this is where our main character enters the story. A Yugoslavian astronomer and mathematician named Milankovitch. Way back in the early 20th century, long before anyone had seen an ice core, he dedicated his entire life to calculating, by hand, how tiny, slow changes in Earth's orbit could completely change how much sunlight hits the planet.
What Milankovitch figured out was huge. It wasn't just one simple thing. He found 3 separate, distinct cycles in Earth's orbit, and each one operated on its own epic, multi-thousand-year timescale. It's the way these 3 rhythms combine, sometimes adding up, sometimes canceling each other out, that creates the grand pattern of ice ages we see in the history books.
So here they are, the 3 key moves in this cosmic dance. We've got eccentricity, which you can think of as the stretch of our orbit. Then there's obliquity, which is the planet's tilt. And finally, precession, which is kind of like a wobble. Let's break down how each of these plays its part.
First up is eccentricity. Now, this is the only one of the 3 that actually changes the total amount of solar energy Earth gets over a whole year. Over a cycle of about 100,000 years, our orbit slowly shifts from being almost a perfect circle to being slightly more of an oval or elliptical. And you can see what that means. When the orbit is more stretched out, we spend part of the year farther from the sun and part of it a little closer. The change is pretty small, but it's enough to tweak the total amount of energy we get. And guess what? It lines up almost perfectly with that dominant 100,000-year beat of the major ice ages.
Okay, next we have obliquity. That's a fancy word for the tilt of Earth's axis, which is the whole reason we have seasons. Over a 41,000-year cycle, our planet's axis kind of rocks back and forth, from about 21.6 to 24.5 degrees. Now, this one doesn't change the total energy, but it completely changes where that energy goes.
And this is why it's so important. A greater tilt means more extreme seasons. The poles get blasted with sun in the summer and are plunged into darkness in the winter. A smaller tilt means everything is much milder. So obliquity is basically the control knob for how intense our seasons are, especially up near the poles.
And last but not least, we have precession. The best way to think about this is like a spinning top that's starting to slow down. It doesn't just spin perfectly upright, it has this slow wobble. Earth's axis does the same thing, tracing a big circle in space over about 23,000 years. This wobble determines when our seasons happen during our orbit around the sun.
So what this wobble really does is decide, say, whether the northern hemisphere summer occurs when we're closest to the sun, which gives us a short, hot summer, or when we're farthest away, giving us a longer, cooler one. It's like the fine-tuning dial for the seasons.
Okay, hold on. We've got the stretch, the tilt, and the wobble. But these are really subtle changes happening over thousands and thousands of years. How in the world does that lead to glaciers 2 miles thick crawling across entire continents, right? That's the missing piece of the puzzle.
And this is where Milankovich's idea was just so brilliant. He realized the key to starting an ice age isn't a colder winter. Most people think you just need more snow, right? But the real trigger, the secret ingredient, is a cool summer. Specifically, a cool summer in the far north, where all the land is.
Because if the summer isn't warm enough to melt last winter's snow, that snow sticks around.
And when that snow sticks around, it kicks off this powerful chain reaction called the ice-albedo feedback loop. It works like this. First, the cool summer lets the snow survive. Then, that bright white snow reflects way more sunlight back into space than dark ground does. All that reflected energy leads to even more cooling. And of course, more cooling means even more snow can stick around next year, which reflects more light, which causes more cooling. You see where this is going. It's a runaway train that can slowly but surely push the whole planet into an ice age.
Understanding this slow, natural process is so important for putting our current situation in perspective. Milankovitch cycles are what we call a natural climate forcing. They change the planet's energy balance over geologic time. What we've done is introduce a totally new kind of forcing, an anthropogenic one, from greenhouse gases. And the biggest difference, the one that really matters, is the speed. The natural rhythm works over tens of thousands of years. Ours is working over decades and centuries. It's a completely different ballgame.
This timeline just nails the shift perfectly. You've got Milankovitch in the 1920s finally giving us the theory that explained Earth's deep climate past, and then just a few decades later, in 1958, a scientist named Charles David Keeling starts measuring CO2 in the atmosphere, and he gives us the first hard proof of a new force that is going to define our climate's future.
So that leads to a really interesting question, doesn't it? If we could just ignore all human influence for a second and just look at the natural cycles Milankovitch discovered, where are we? When is the next ice age supposed to start?
Well, the answer, based on everything we know about orbital mechanics, is not for a very, very long time. It just so happens that right now we're in a period where Earth's orbit is almost perfectly circular. That means the orbital pull needed to start an ice age is super weak. The models show that it won't be strong enough to even begin the process for at least another 50,000 years.
And that leaves us with this one final, pretty profound thought. We did it. We basically cracked the code on Earth's ancient, majestic climate rhythm. We figured out the pulse. But the massive amount of greenhouse gases we've pumped into the air is now starting to overpower that natural beat. So the big question isn't when is the next ice age anymore. The question for our time is, have we pushed the Earth's climate off its natural track and created a new, unpredictable rhythm all our own?